So then actually I will try to be not that technical, so I apologize if it was a bit too technical in this model of categories and so. So I will use what we did, I would say did yesterday, just as a final result at some point, but I will not go in this technique further, right? So then today I guess it will be more easy to follow, think. So what I like to, today we will prove this theorem. So what is the theorem? Well, we will not prove very well complete. There are 3 statements or even more. Barratta-Priddi-Kwillena theorem. So this is a story that if I take n, which is the joint union over n greater or equal than 0 p sigma n, where sigma n is symmetric group on n strings, and then this is a classifying space, so then this, well, b sigma n is, well, we have several notations, so it's something like realization of what we call xm and so on. So this is actually simply, we first construct simplicial set by a group, and then we take the geometric realization. And this is a monoid, strictly associative monoid. Where the monoidal structure comes from the, well, we have a map on the level of groups, sigma m plus m, and then when we pass to b, we get b sigma m, b sigma m to b sigma m plus m, and then it makes it strictly associative monoid. And one thing which I will explain a bit later after I state I give you a statement of the theorem, is that this is homotopically commutative. But this I will explain in just a second. Homotopically commutative. Yeah, so that this product actually is commutative. It commutes up to homotopy and coherently homotopy commutative, whatever it means. Yeah, so in that statement, this theorem says that Barratta-Priddi-Kwillena says that if you take B from this monoid now, and then the loop spaces of this, then it's homotopically equivalent to what is called omega infinity of sphere infinity, which is colim of omega n Sn, as I explained in the very beginning. So the full truth is that, which I'm not going to explain, is that this thing is group completion. So, well, I will say something about that at the end. Group completion of M. So then somehow if we have M, which is not connected topological monoid, then we can often make it where it's not connected and pi 0 is not a group. M is not a group. Then we can, in some cases, not always, we can make this pi 0 a group. For example, if we had a discrete monoid, then this construction is, well, something like you take free monoid, free group generated by this monoid if M was a discrete, and then you take quotient by relations that M1. Yeah, so then M1. Yeah, you say something like. Yeah, so something like M1, M2 in monoid, M1 minus 1, M2 minus 1 is equal to identity, something like that. So then you impose all relations which you have in this monoid, and then it's actually a group. And this is some canonical thing. So the statement is that in some cases, which I talk about later, you can do the same thing for topological case. If M was not a discrete monoid, but topological monoid, you make pi 0 a group. In some cases, and this is called group completion. But so the truth is that it's group completion in this case, but this I'm not going to prove. I prove only that. And I will provide a statement about group completion and maybe something more in the end. So this is a theorem which I'm going to prove.
Can you say group completion is a factor from which category to which category?
Well, let me tell about it later, because now I don't want to spend time. Otherwise, yeah, we go to some technical stuff. You can ask me after the talk, please, if you like. Yes, so then, what is the idea? idea is that construct a gamma space. So as I said, it's homotopically commutative. I will explain it in a moment. And the fact that it's homotopically commutative gets hints that it could be restriction that, yeah, I will tell. So construct a gamma space, which we call B sigma, with the following properties. So the first property is that B sigma of 1 is exactly my monoid, n B sigma n. And the second property is when I recall that we have a restriction from I from gamma to delta, and then we take this gamma space and restrict it is homotopically equivalent to the standard simplicial space which we construct out of monoid. So this is what I call XM, yes? It's standard guy which I can construct by associative monoid, yes? So the XM in power n, in n is m in power n. So then there exists such gamma space. And Sigal constructs such gamma space, and then he works with this gamma space and then uses that adjunction on the homotopical level between connective spectra and gamma spaces, which we did. So then the idea is that actually we convert the entire statement to a statement about gamma spaces at the end. Yeah, so but this will come a bit later. So first of all, let me explain, because I think it's very important, why this is homotopically commutative. Well, I will not literally use it, but I guess that it's important for understanding what goes on. So I recall that at the end of last lecture, I defined for category C, say, small category, say, I introduced its nerve, which is a simplicial set. And I recall that the nerve of C in N was all sequences of composable arrows of length N, yes? So then in particular, length N. So then in particular, if my category C has a single object called denoted star, and home C from this object to object is monoid, my monoid, that this construction N of C is the same that this XM which I defined before. Yeah, so then property which I use, which is very elementary if you look at this definition, that if I have just product of this two small categories, that I get a product of simplicial sets. So which means by definition that in each n, for each n, you have the product of n components here with n component here, and the all operators acting diagonally. Yeah, so then also we know, I recall that the functor of realization also preserves products, right? Preserves finite products. And finite limits, actually. Yeah, so the conclusion from this and this statement is that the realization of C1 times C2 is product of realizations as topological space. And this is actually has some nice consequences. For example, assume that we have two functors from F to G, from C1 to C2, and assume that there are natural transformation, eta, which is natural transformation from F to G. So then I claim that the corresponding maps on realization F and G, which map from BC1 to BC2, are homotopic maps of topological spaces. Well, I don't know, I guess that it's very simple proof, which I cannot resist to tell you, although it takes some maybe 3 minutes. So the idea is...
It is natural isomorphism, right?
natural transformation, not natural isomorphism. They are homotopic for any natural transformation. This is the point. Not natural isomorphism. You will see proof in a moment. So I just, first of all, I just reinterpret what this means. That this I have two functors and natural isomorphism. So let me call I1 the following, or maybe I1, the following category. It has two objects called 0 and 1 and a single morphism. Then have such data, it's the same that a functor, say H, from I1 times C1 to C2. I guess it should be clear. Because restriction to 0 and restriction to 1 gives me two functors, and somehow this morphism gives me a natural transformation. So then this data gives me such functor H, and when I pass to nerves first, using that nerve commute with products, I get nerve of I1 to C1 to nerve of C2, and then I pass to realizations, and then I make use of normalization of this nerve of I1. It's a standard unit interval, I guess at 0, 1 or so, delta 1. Yeah, so then you can do it as an exercise, and then we have that we have this delta 1 or I standard intervals realization to C1 to C2. And this gives me actually a homotopy between these two functors. So it's actually due to either Quillen or Sigala, and that's written in the first few pages on the paper of Sigala, algebraic case theory 1. Yeah, so then, but actually they refer to each other. I mean, Quillen and Sigala, about who invented it. Well, there is some simple homotopy of categories in this way. Yes. So anyway, how we can use it? So, for example, we have we have sigma n and sigma m, and we have actually two functors to sigma m plus n, right? Where on objects we can put it in correct order. So if alpha is here and beta is here, then we could put either alpha beta or beta alpha. So both are transformations. Yeah, so then it's two functors from this bifunctor, so functors from this product to sigma m plus n. So basically the difference is on morphisms, of course. Yeah, so okay. So then these two functors, so let me call it f and g. There is natural transformation between f and g, which is given by conjugation by some permutation which changes the first n and last m elements of m plus n elements, right? So standard one. So then it follows that actually these two, that there is homotopy between b sigma n, b sigma n times b sigma m. So then I have two ways of taking product which come from this order and these two products become homotopic. So then I have, for example, standard product to b sigma m plus n, and the product which is previously switched somehow. So I say m and m sigma, right? And the idea is that m is homotopic to m sigma, so this is homotopically commutative. And then actually it's also commutative up to higher homotopies, and one point was how to formulate it, how to state the statement. And actually the idea is that we can construct a gamma space.
Here we view this symmetric group as categories with one object.
Huh?
Here we view this symmetric groups as categories with one object.
Yes. We always with monoids, with groups. Sorry that I did not mention here explicitly. I mentioned it somewhere here. Yes, good. So then let me go a bit further and construct this gamma space. So the idea that before constructing this gamma space, I construct a gamma category. So I recall the definition. So I gave the definition of you, I think, lectures previous to the last or so. So then we have a functor from gamma O to hat, where these are, say, small categories, and with the following property that gamma from some x, where x from 0 is just the final category which has one object and only identity morphism of that, and the canonical map, as we usually have in gamma spaces, from xn to x1 in power n, is equivalence of categories in the classical sense. Equivalence of categories. Yeah, so then we construct a gamma category. Yeah, the first remark, very simple I think from what we have here, is the following, that let C be a gamma category. Be a gamma category. Then, if we take BC of n, define it as B of C of n, then it is a gamma space. Yes, so then somehow we use the fact that realizations behaves well with weak equivalences. This is actually some subtle point which I explained, well, we didn't explain, I mentioned several times, but without this subtle point, if you take a gamma category and element-wise apply this classifying space function, we have a gamma space. So first of all, yeah, we have to check basically that fact that BC n to BC1 n is homotopy equivalence, and then we deduce it from the fact that this thing is equivalence of categories. Well, I think that, yeah, I think I can skip details here because we already stated everything. Okay, so then now it's construction. So what we are actually doing, so how we construct this category and so on. Gamma category. This is actually a very interesting story because, yeah, so then somehow we can do it morally from any model, from any symmetric monoidal category. But actually the construction of Sigal, it's not really sort of bar construction, as for example construction of Thomason later, which he did just as a bar construction. So what Sigal does, let me give you some examples. So for example, for C1, he takes just, well, the category whose objects are, so we consider now the category of finite sets. Morally we consider it as a monoidal category where the monoidal operation is the joint union of sets. And then this one is the category whose objects are just finite sets, and the morphism isomorphisms. So then it's not connected category in this sense. Morphisms, isomorphism of finite sets. So then for each n we have a finite set of n elements, and then the morphisms are isomorphisms from n to n. All isomorphisms, all permutations are in gamma. So then actually if we take the classifier, if you take this C1, it's actually the joint union of sigma n as a category, right? Yes, and then when we take the classifying space, we exactly take BC1, it's exactly the joint union over n of B sigma n. So exactly what we want to get. Yeah, but actually then Sigal wants to extend it to a gamma category, and let me give you an example how it looks like in C2 and maybe in C3. So then, for example, in C2, he considers such diagram of finite sets. So these are embeddings of finite sets such that this diagram is co-limiting cone somehow. So this diagram represents A12 as a direct sum. In our case, it's the joint union. But we consider it as a direct sum of A1 and A2. So it means actually that there are, if we fix here M and fix here N, then here of course as object would be M plus N, but here there are many different choices of this maps from n to m plus n and n to m plus n, such that all of them represent m plus n as a sum of m and n. So it could be any, somehow it could be any embedding, so let phi1 and phi2 be any embedding such that images of phi1 and image of phi2 are disjoint. Yeah, and then of course the union is all m plus n, so we somehow can embed it in arbitrary ways such that the images are disjoint. And all such diagrams represent m plus n as a sum of m and n. So there are many such diagrams, and we actually like to use all of them. The idea is that basically we like to use these two, but somehow, well, what Sigal does, he constructs, of course, this and these are particular cases of this PS phi1 and phi2, but he considers all many other things when they are permuted anyhow with disjoint images, not only these two. But the idea was to have these two, right? So okay, so then actually maybe here it's example for C of 3. It's some diagrams like that of the following type. So we have A1, A2, and I3 final sets. Here we have A13, here A23, here A12, and then all these diagrams. And here is A123. Yeah, so something like that, like that, like that, like that, like that, and like that. And the idea is that each straight line, either this, for example, or this, however you like, represents the object in the middle as a direct sum of the objects in the end. So each straight line somehow represents something like that. Call it 1, 2, 3, represents 2 as a sum of 1 plus 3. So, yeah?
And morphisms in either
isomorphism, which commutes with all that, right?
Okay.
Yes. So now I give you formal definition. Okay. So because it's just examples, I give you a formal definition how it is defined. Okay. So let me maybe this I don't want to erase because it's idea.
formal definition for Cn or
Yes. Exactly. Yes. Yes. So gamma category, right? And then I get gamma space by taking the classifying space function.
by direct sum, do you mean disjoint union?
Yes, it is categorical direct sum, right? In the category of finite, it's categorical direct sum of finite sets. It's disjoint union. But in principle, we can, what Sigal writes that we can use any category with direct sums where a choice of direct sum is usually it's not fixed, or direct product. But in fact, this works for any monoidal category, and in symmetric monoidal category instead of that. But this is more complicated. Literally, it's not written, in my opinion, in Sigal paper, but it's known. Yeah, so then, so how it is defined? So then we consider by P of S for S final set, and we consider this is a category of all subsets, objects, subsets of S, including empty and entire S, and morphisms are inclusions. So the first lecture in the definition of gamma, I use notation P of S for just a set of all finite subsets, and here I underline to stress that in this case it's a category. So the objects are the same, but now I have morphisms which are inclusions. Yeah, so and then I consider functors. So let C be a category with direct sums. Is like finite sets as our main example. And we consider the categories, let me call it C of n. It's a category of functors row, oh, no problem. Of functors p underline of n to c, which its objects which send disjoint union to direct sums of any objects. So these are objects, and morphisms, so it's objects.
Direct sum is co-product?
Co-product, right, of objects, we call it direct sum. Yeah, so for example, here both are, here we use the joint union and for that, but maybe it's the joint union in different categories, I would say. Here we have if we have two subsets in N, then we can subsets send disjoint union. The disjoint union, so if you have two disjoint subsets, yeah, so this is disjoint subsets, and then the disjoint union, then it should be taken to direct sums. And morphisms are isomorphism of such things. Isomorphisms of such functors. Yes, actually, for example, if you look what I have for small m, for example, for C1, it's clear that I get exactly that, right? Because there is empty condition that the joint union assent to direct sums. But if I look, for example, at C2, then I have P at this row of 2, which is a category where objects are empty set, then 1, 2, and 1, 2, right? So then this is sent to some zero object whatsoever, so you don't care about it. So the interesting information is about 1, 2, and 1, 2, and these are sent exactly to A1, A1, 2, and A2, and we have embeddings, right? So then the joint union of 1 and 2 is A1, 2, and this the joint union, it should be sent to the sum. So this is exactly, but there are many ways, as I said here, to represent, say, n plus m as the joint union of them. And we consider all of them, so, because it's a functor. So then we have embedding from 1 to 1, 2, and we have embedded some map, yeah? So from 2 to 1, 2, and they should be reflected in this functor. So then we have such diagrams. And this, the maps of finite sets, or generally in objects to which the standard embedding maps, there is quite a lot of choices for them, as I...
Sorry, how in this formalism it starts out that the images are disjoint? We allow...
What is images? What do you mean?
Here in C2, we're required to image of A1 and E.
No, this is just a categorical sum. Here in the image, we cannot care about disjoint. So about disjointness here, the condition is that it takes here disjoint union of subsets. So I mean that if subsets intersect, then there is no condition.
Of course, but in C2,
then it's just disjoint, it's sum. This disjoint union is categorical sum. It's direct sum part. It should take disjoint union to sums. In category of finite sets, a sum is the joint union of sets.
Of course.
Yes, and?
But
yes.
as we require morphisms to be inclusions in P cross of S.
Yes, then.
So in its representation, probably we have a situation when A1 and A2, let's say in the left part of the code.
No, we require that if 1, 2 is the joint union of 1 and the joint union of 2, which is the case in our category, right? Then it should imply that A1, 2 is categorical sum of A1 and A2.
There is a morphism from 1 to 2.
Yes.
There is a morphism from 2 to 2. And so
yes,
as we represent, we get A1 and 1 includes into Like, wait, 2 into brackets.
I don't understand. Do you understand?
Why do we have a morphism from 1 to 2?
It's inclusion.
No, from 1 to 2 we don't have anything, because inclusions, look, we have set. The elements of sets are the set n, where n is equal to 2, is 1 and 2, right? We have all subsets of these two element set, which are 1, 2, empty set, of course, and then 1, 2. The set of two elements. So what do you mean? I don't understand.
Okay, probably.
Yeah, probably it's clear now, right?
Okay.
Okay. Yes. So then, okay. So then actually it gives rise to such diagrams, and what is important? This actually is a gamma category. So well, for any category with direct sum, even there is some adaptation of this construction for any symmetric monoidal category, but it's a little bit difficult. So, for example, if we have symmetric monoidal category any, then C2 should be defined as quadruples, I would say x1, x2, x1, 2, and alpha, where alpha is isomorphism from x1, 2 to product, monoidal product, and x1 and x2. But higher definitions could be more complicated because we have to use the associator and the gradient. But anyway, in this way, we can formulate it generally for symmetric monoidal category and prove that it's a gamma space. Yeah, so okay, so this is actually the definition, and the claim is that it's gamma category. So let me something. So the claim is it is a gamma category for finite sets or for any category with direct sums. So it is a gamma category. So basically it's clear that this condition for x0 is fulfilled. So then actually, well, more or less by definition. So then what we have to check is this condition, that C of n is mapped to C of 1 in power n, its equivalence of categories. So how we can see it, for example, for this example. So if we have A1, here A12, here A2, and here we take some other thing, yes, so some say A1 prime, and here it's isomorphism A2 prime, and here it's isomorphism, and here we have, well, in principle, what Sigal does, he considers a skeletal model of finite sets. So then he considers, say, here just a single n for n element set to avoid some mess. So let me do it in the same way. So we have, for example, for finite sets n plus m, and here m, and here we have some isomorphism. Here we have some isomorphism. Here we have also to n plus m, and here some isomorphism, right? So the claim is that we project this thing A1, A2, A12, and this maps I1 and I2. So we project it just to A1 and A2 pair and forgetting about these maps. So then the claim is that in this way we get an equivalence of categories. So because the idea is that as soon as we fix this map F and G, which are isomorphisms, so what doesn't matter in fact, so then we can, using the fact that it's a categorical sum, we can consider such composition, and that's by universal property of sum, we have unique map from n plus m to itself, which fulfills to commutative diagram, and certainly it is an isomorphism. So then it means that that having the that as objects, as on the level of objects, so then it follows that actually, then it follows that any object is actually isomorphic to the standard object, right? Where we have, for example, this way of putting alpha and beta. So anyway, we use this universal property of this direct sum things to see that in general we have an equivalence of categories of that form. equivalence of categories. Yeah, but actually Sigal writes some formulas for that. For example, for not only, well, for example, he never used it, but for example, for B sigma, let me call it B sigma underlined. For 2, he has the following formula that it's union over Mn. Here we have B, not B, but actually E. It's an exercise, I would say. E sigma M times E sigma N, where E is that thing which I, in the first lecture, denoted by bar M point. So this is contractible thing, right? Such that the quotient by the group, it's B, it's actually yes, so then sigma, E sigma M plus N here. So then, and the symmetric group acts E sigma M plus N, and then we take the quotient by the symmetric group sigma product of sigma M times sigma N. So then actually this space as it is defined looks like that, which we can see. But then this categorical, or I don't know how you can prove it from this formula if you like, calculation shows that this is equivalent actually, homotopically equivalent to B sigma, to B sigma of 1 times B sigma of 1, where we ignore these intermediate terms, and B sigma 1 is given, I guess, by the formula which you already know by heart, B sigma N for N. Yeah, so this is actually the construction. And what is important in this construction is that in this construction, what is important is that when we restrict this gamma category to delta, so we can restrict it to delta. So then let me erase, maybe I'll erase, okay. Let me erase something here, maybe. So as well as with gamma spaces, I can restrict gamma category to delta category, right? I have a functor invading from I, from delta to gamma, and I can take I upper star of, well, call it sigma, this gamma category called sigma. Yeah, then it becomes a functor from delta op to hat. And then the claim is that this functor, actually, when we take it realization, well, even before realization, so that this category is equivalent to the standard one. So the claim, which is used actually in this interpretation of Barratta-Priddi-Kvillena, is that when we do that, when we restrict to delta but not before, we get that I sigma of n is equivalent to sigma of, well, 1, so yeah, sigma of 1, so in power n. Just, how to say it, yeah, well, equivalent and the more, yeah, well, in a sense we have such equivalence there as well, but what I mean, actually, what I like to deduce is when I compute realization of this B sigma, right? Then actually in, then I like to know, yeah, that it's the same thing as realization. Yeah, so what I mean, so let me tell it more precise. So that's what I mean, that this, when I take realizations of this sigma underlined, it gives me B sigma 1, B sigma 2, right? So then it's somehow a gamma space. Gamma space. Then I take realization, it's called sigma, B sigma. So this is gamma space, gamma op two spaces. And then I like to take realization of So realization of B sigma. Yes. So then I take realization of all these guys, meaning that firstly I restrict it to delta, and then take the realization of this simplicial set. And then the claim is that this realization is actually B of this monoid, B sigma 1. So this B sigma 1 is that my monoid, so it's a strict monoid. And so then actually when I consider it realization, that is homotopically equivalent just to realization of this particular monoid. A priori, these higher guys which can also contribute and so on, but the matter which I have to check actually, the spaces themselves, they are equivalent to, of course, to B sigma 1 and power 2 here and so on, but I have to check that that under these equivalences, actually the operations which I have look like just simplicial operations in this monoid. So here, morally, what I use here in this sort of speculation is that my monoid is a honest monoid, associative monoid, but it's the homotopic things are only when I consider commutativity, right? But if I forget about commutativity, because operations in delta, they know anything about commutativity, they only use associativity. And associatively, I have a strict monoid. Yeah, in principle, for general gamma space, such speculation wouldn't work, because for general gamma space, my formula from that x2 here, right, it maps to x1 to 2, this is homotopy equivalent, this is x2, doesn't give me honest associative monoid structure on x1, just something up to homotopy, but here I make use that on x1 I already have a honest monoid, and then I can deduce from here that the realization of this gamma space is the same that realization of this topological monoid. Yeah, this is very nice. So actually this is only what I need as a preparation, and now we prove this theorem and give some interpretation, so then I have enough time, I hope, and this is very nice. Okay. So now I can erase probably here, because we fulfilled all these conditions, right? What I said just now is the second condition. Then when I restrict to this V sigma, but now it's underlined, to delta, I have this bar construction of my monoid.
We want to prove that this result on the left part, that realization of B sigma is specifying space of B sigma.
Of that monoid, right? And then, yeah, and this should be deduced from the fact that B sigma 1 is, unlike in general gamma, for general gamma space, it's already strictly associative monoid, and we prove it categorically. So we somehow firstly make some categorical equivalence of that and show that the simplicial operators act.
But by Sigal theorem, we for any gamma space, like even with associativity up to homotopy,
yes,
we knew the adjuncted result, that the loop space of the left one is weakly equivalent to B sigma 1.
No. What I mean here, yes. What I mean here, that loop space.
We use it somehow in our proof.
No. It's very tautological. You just use the fact that it's somehow a strictly associative monoid. That technical lemma has nothing to do with the statement. We just first, but to prove it, we first look at this categorically. Okay. So just first of all, we take what happens when we, because categorically we also have some monoidal category with identical associator. If you look only associative, not as symmetric monoidal category, but as
regular monoid. Regular monoid, if we take like
yes. So then it's when we pass, so then first such sort of statements it's better to prove categorically. Actually, there is some paper of Thomason where he even all Sigal stuff does categorically, so all these higher classified spaces and so on. So anyway, so then, but this is for sure. So then, what I like to say now, that now we return to what we had last time without this, maybe some this annoying technical details, but basically what happened is that we had this category. We have homotopy category of gamma spaces, homotopy category of gamma spaces, and we have SP, the stable homotopy category of spectra. And what we had that spec of BA, for A gamma space, and X spectrum. We have that this one was equivalent to the functor, had right adjoint functor, which was from A to what I called R of X, where R of X was a gamma space, not special in general, but so we defined, I just recall how we defined it before passing, but just on the nose definition because we use it. So it's a gamma space whose value on n is this internal home in which takes values in topological spaces from product of sphere spectrum to n, it's called product to x. Yeah, and then we had from general property, homotopical property of this internal home, which we claimed without proof. We claim that, which is important now, I just will not further comment with that, sorry, not vibrant, but I will avoid it. Omega spectrum, I have that there is embedding from S in wedge product n to S in Cartesian product n, and I claim that somehow as this is some vibrant in general, but in fact what I use that it induces weak equivalences on home. So then home of Sn to x, the restriction to home of Sn to x. This is homotopy equivalence from the fact, in generally not, but for vibrant spectrum, yes, it is applied for, well, here for general embedding of what's called vibrant spectra, but it doesn't matter where the structure maps of spectra are closed embeddings. But this is equivalent, homotopically equivalent to home of S in first degree to x in power n. Yeah, so this is actually what we need. So this for vibrant spectrum we have, so then if x is vibrant, we have omega spectrum, we have a special gamma space. Meaning that we have this property, Rx, yes? Good, so then, yeah, so then now what is the second idea of the proof? So we make use also that, well, claim which I stated yesterday that, well, this SP has two interpretations. Either it is homotopy category of all spectra with stable equivalences, right? Stable equivalences mean that it's isomorphism on all homotopy groups of spectra, or otherwise it is homotopy category, full subcategory of omega spectra, and here we have strict equivalences. So this is another story which I'm going to use, and now I like to apply this adjunction to my case. So then I have SP to B of, I guess everyone knows what B is, right? So this is actually that single B, but we had interpretation through n-dimensional spheres, for which I use argument of Anderson, which is very nice. And then it follows from this argument immediately that it has right adjoint of that type. Yeah, so then B of B sigma to X, yeah, so it is the same stuff as in A, from B sigma to Rx. Great. Yeah. So in principle, we are going to due to this interpretation, equivalence, we will assume always that X is omega spectrum. It's no loss of generality because it's even better, because then we can consider strict weak equivalences of spectra, which I recall means that if we have some spectra, then weak equivalences are just, strict weak equivalences are just some maps like that, which commute with maps of structure maps of spectra, such that all that stuff are weak homotopy equivalence, but Sigal works with strong model structure, so it's strong homotopy equivalence. So this is very manageable thing. So then actually also one thing which we are going to know, that there is that if X is any spectrum, well, in principle, Sigal assumes some technical assumption that the maps from xi adjoint to structure maps to omega xi plus 1 are closed invariants. But in principle, it's not very essential, but to avoid homotopy co-limits, so embedding, so then in many examples, in all examples, but it's not essential, fulfilled. So then it follows that we have canonical omega, we have omega spectrum x prime, omega spectrum, such that with embedding of x to x prime, and this is stable equivalence. So then this is, I will give a formula for x prime, equivalence. So that means that, so the formula is the following, that xn is actually xn union omega 1 of xn plus 1, union, I mean in the sense of embeddings, right? So then we take colim, I would say colim over I greater or equal than 0, omega I xn plus I. Yeah, so then we make use that we get closed embeddings here, and therefore when we compute pi I stable group of this colimit, we can compute homotopy groups with colimit sign, and then we get something which is exactly the homotopy groups of stable homotopy groups of original spectrum X. So then what we have this construction, and we can see that this embedding induces isomorphism on stable groups, and this is a canonical replacement. So then in particular, if we like to work here, which we do, we can replace any spectrum to this way canonically. For example, coming back to the theorem of Barratта-Priddi-Kвиллена, we can see that if we start with a sphere spectrum, right, then we get a spectrum sphere head with I term, which is so colim of omega or n term, which is colim over I, omega I plus n, n, right? So then in particular, the zero component of this sphere spectrum head, it's exactly the topological space. It's exactly omega infinity as infinity. So we are getting very close to the initial statement. So yeah, so then actually what Sigal proves in that sense, he likes to prove that A of B sigma in the right hand side to Rx is isomorphic to A of sphere spectrum to Rx for any x. Because then, if we use this interpretation and this fibrant replacement of everything, we conclude, if we know that, so we are going to prove this statement now. Not now, but after some comment. But actually, the rest of lecture would be a proof of this statement. But yeah, what would follow from this when we use this interpretation, that if you take B sigma and apply this head construction, the fibrant replacement, I would call, that is homotopy term-wise, strictly, in this sense, homotopy equivalent to sphere spectrum when we apply the same construction. Yeah, so then what it would give to us, look. So then,
So could you repeat please what
yes.
head means?
Huh?
What does head mean?
Head takes xn, its nth component, its colimit, So you start with xn, then take the union of omega 1 xn plus 1, and these are by assumption if we impose it, but in general we should take some telescopic construction like homological.
It's a finite replacement of x?
Yes, yes, so if we take xn plus 2 and then we take the union of all these guys in the assumption of the fiber the closed embeddings, then we get actually some spectrum which we can easily see, and the claim is that the canonical embedding of x to this, just as the first component, actually induces isomorphism on stable groups. And to that we make use that this is closed embeddings, because this is some technical thing that if we have a compact space and we have take home to column of closed embeddings, and here it is important to say, well, as xi, where this is closed embeddings of topological spaces, and here it's compact, then it's actually column of this k of xi somehow this whole. So this we use for k equal to spheres, right? And this is important. So for homology, it also holds, but for homology we should firstly use that it's closed embeddings, and then the statement that equational colimits, or in general fiber colimits, commute with filtered colimits, in particular that sequential colimit, commute with finite limits, because when we take compute homology, we also take kernel at some place. So firstly we use the same stuff, and after that here when we do this fundamental group, homotopy groups, we don't need nothing more, but when we do something the same for homology, we also need the theorem that, for example, kernels commute, which are limits. Kernels are limit, and this is colimit. In general, they are not commute, but in this instance, they commute. So all colimits commute with finite filtered colimits commute with finite limits.
So is it true that this head construction from some spectra to omega spectra to a stable equivalent omega spectra?
Yes, yes. So then in
from
this
one model of this SP to another model of this SP category.
exactly, yeah. We work with it doesn't matter. But if you work with this omega spectra,
It's
because
better to our purposes, like as omega.
what?
So we want to work in this lower model of this spectrum.
This one, exactly, yes. Then we take for x any fibrant spectrum, and we take the fibrant this omega spectrum replacement of that, and the conclusion Sigal proves this statement, and if we proved it, then the conclusion is that this fibrant replacement are strictly homotopically equivalent. And strictly equivalent means term-wise equivalent.
Yes.
So in particular, we can compare the zero term of this equivalence. So the equivalent spectra. So look, then what we have here. So then, yeah, so then if you take sphere spectrum, it's written, yes, so then if you take sphere spectrum and 0, then it's just omega infinity as we explained, right? Mm-hmm. And then if you take this B
sigma under
yes, B sigma,
mm-hmm.
yes, then we know that for any gamma space, it is, then for any gamma space actually, gamma space A, so what we have that omega of B, in first B of A is, so B second is B1, B first of A, and so on. Omega of B3A is B2 of A, yes, homotopically, because of this technical Sigal lemma.
Because of Sigal.
Exactly, yes, because it becomes connected gamma spaces, in particular group-like, very special.
Yeah. After
the second step, first step, right?
Yeah.
So the only problem is with this map from sigma A to BA, because the B in power 1A, yes, the first specified space. Because from this Sigal technical lemma follows that all the rest are homotopy equivalent. So then if we apply this construction to this particular spectrum, that it's very easy to do. We only need to take loops of this B1 and that's it, right? So then I mean that if we have B, this spectrum B, of any gamma space in fact, and take this hat, then it will be just omega of B1 of A, and that's it. Yes? Yes. So in our case, B1, as I said, from that equivalence when I restrict to the delta, right, it's actually B of this monoid, B sigma n. So then we get that B sigma hat 0 term is omega B of this monoid B sigma n. So then if we know this claim, which Sigal proves, that it would imply exactly the statement which I announced. So namely it would imply that omega B of union of over n B sigma n, which is actually 0 term of B sigma hat and 0, right, is equal, homotopic, equivalent to, the 0 term of sphere spectrum hat 0, which is omega infinity as infinity. So then we get what was claimed. So it reduces to proof of this isomorphism. But now I like to make some simplification of it. So of course X will be a Fibron spectrum always for these needs. Then I need to, first of all let me look on the right hand side. So then it's clear that for any spectrum, the home from sphere spectrum to X, any spectrum X, or yes, so I think it's something wrong. What is it? I know it's correct. It's just a second. Yes, it's that, right? Just a second. Yes, it's like that. Yes, and then we. Yes, it's correct. Yes. So just. X is a gamma space, right? Correct. Yeah, so this is a gamma space then, right? So then if you have here, it's a gamma space, but actually if you have any, so just yes, okay, but just a bit confused somehow. Just a second. No, of course I like to, just a second. So I think here it's a mild confusion because what we know from a junction is this thing, right? And if you like to know that this is equivalent to sphere spectrum, right? Then what we get? Then that actually what we like to show then, if you want to prove that it's a sphere spectrum, we like to prove that in spectra from S, sorry, it was a bit strange, I guess, something, to X is equivalent to that, but then I use my junction and then I write it down that it's actually B sigma to Rx, correct? This is correct, right? So where X is a spectrum. So what was written here was, I think, different. So this is correct. So because I want to prove that this spectrum can be replaced after this omega replacement by sphere spectrum, and this I know from the junction, so I have to prove that. Because if I so I have to prove that. Then then it would follow. But actually this one, it's exactly pi 0 of x, of spectrum, right? And as x is fibrant x, then it's actually pi 0 of x0. Because for fibrant spectrum, for omega spectrum, pi 0 of this spectrum is just pi 0 of 0 component. So then, yeah, but let's look what we, so then we have to prove actually that in A, from B sigma to Rx, yes, it's pi 0 of x. Yes, which we know that for fibrant it's pi 0 of x0. But I have something as follows, that I can now write pi 0 of x. I like to somehow rewrite it through this Rx1, right? So then I claim, just which simplifies greatly the thing, then pi 0 of x can be replaced for fibrant x is the same that pi 0 as topological space, now not spectrum, of Rx1. So this is a claim that for any fibrant spectrum x it is the case. So then it will be very nice for me because then I eliminate this Rx completely. So I'm going to prove that, and after that I prove that if I need to prove, then I can replace this by any special Gamma space. A, it's actually pi 0 of A of the first component. This is what I'm going to prove as soon as I establish that. Where A is special Gamma space. So then the idea is that in this trick I can eliminate this spectrum S and work completely with Gamma spaces, right? So what I mean here, what is Rx1 by definition? It's home from sphere spectrum to X, right? But for any suspension spectrum, because what does it mean? That I have S0 to, well, X0, then S1 to x1 and so on, which commute with the suspension function. Should be strict map of spectra. So meaning that, if I have f0, f1 and so on, that I mean that if I apply sigma s0 to s1, for example, then I take here f1, here x1, here x0, sigma x0, here sigma f0, then such diagrams for any I should commute. But then, as here I have identity, isomorphism, then all the sequence is defined by the first component, f0. So then it means that this is actually x0. No, it's not x0, but it's somehow formed in topological space from s0 to x. And then if I take pi 0, so this is actually the entire x, because I work with base situation, S0 has 2 points, one of which is based, so that is entire x. So what I'm doing with is pi 0 of x0. So pi 0 of x0. If I, write down what I have in this right-hand side, right? Pi 0 of x0, and I should compare it with pi 0 of x, which is stable homotopy group. And here is pi 0 of single x0. And here I make use that I deal with omega spectrum. Because for omega spectra it is the same.
Okay.
Because what is stable is I should take pi 0 of, so then in general, what is pi I of spectra? There is some sequence that pi I of xi, then pi I plus 1 of omega, yes? Yeah, probably.
Omega.
Yeah, but anyway, so I just a little bit confused. So, but anyway, it's clear, yes, I showed it once that for omega spectra, you have only all isomorphisms, which when you compute the stable homotopy group. So then the meaning that this, I have just x0 as topological space, and pi 0 this topological space, and here from from this formula, I had pi 0 of spectra, meaning stable group. But for Phi-prime, they are the same. So, and this is very nice, because up to this replacement, I can indeed prove this formula, where A is special gamma space. A is special gamma space, so then I'm completely inside the gamma spaces. I have nothing to do with spectra. So I have gamma space, this B sigma, well underlined as you. So any special gamma space A, and I have to prove this identity, right? Okay. No, I guess it was possible to follow. Well, at least I think all steps were pronounced somehow. Maybe too quickly, I don't know. But you can, if you like, listen. If you have any questions here, maybe you can ask now and then, because now I'm going to switch to the proof.
All the steps are on the different parts of the whiteboard, but they all are.
This is because this is quite small, because compare with 311 room and the blackboard here. So there I use everything linearly, right? So because I can put it
In the
upstairs.
room, the blackboards, like there are 6 blackboards.
Yes. I'm sorry that, but I'm not very good in the sense of this good presentation. Sorry. But anyway, I think it was quite clearly said in my opinion. Now, so then I'm going to prove this claim. This is also very interesting, and here actually this is the essence somehow. The idea that after all this preparation, the claim which we are going to prove, which is in the frame. Sorry? Chris, have you any comments?
Заблудился в лесу.
Yes, okay, good. Yes. So actually, this is quite this is a statement which which is actually, as if you read the proof in the Sigal, you should reflect quite a lot to understand. And my pedagogical idea was that to explain the idea of the proof. Now then I will switch to general case, but to explain the idea how it works, I can firstly take for this A, which is special gamma space, something which I associate with commutative monoid, the story which I started with, right? So if M is commutative monoid, then I have a special gamma space which I started with on the first and second lecture, which in N is M in power N, and so on, right? You remember from?
Yeah, first.
Okay. Yeah, so then I first explain how I can see this for this particular case, AM, because then it's technically easier. And then we will see how we can arrange it in general. So what I'm going to do, actually, so this, I will do it somehow categorically. So then, so let me explain. Just a second. Yes, so I guess it's in there. Yeah, so then what I'm going to do, I will so then I will construct from this sigma n, sigma k, where this is a gamma space I work with. I will define a map to A of k, where A is my AM, but after that for general. Yeah. So the idea, look, maybe I should start with the following. So then first of all I have a map in this direction, and then I have to construct a map in backward direction, which is more difficult. So then in this direction for general A is clear, right? So let me say. So how I construct it in this direction. So then for general A, I have in B sigma, so then I have, for example, B sigma of 1, which is just a single point. And then I have a map from this single point to A of 1. And this gives me some point of this. So then this map, if I have this map F, it gives me F of this single point, which belongs to A1, and then I take its class in pi 0.
Okay.
So this is a map in this direction for general A, which is very clear. So then I like to construct a map of backward direction, which is more complicated. So then for this case, I start with this particular case of AM, right? Because it's easier to explain the detail, right? And the idea. So what I'm going to do, I fix the point A in pi 0 of A1. And then I like to extend it to somehow to such a map. Yeah, so how I do it? Yeah, so then actually the idea is that I can, so this is actually gamma category. So I construct it on the level of gamma categories. And then I pass to B. So, but this is actually gamma space A of M, not gamma category. But then I can tautologically consider it as a gamma category with only identity morphisms. So, well, if I have any huh?
No inclusions.
no inclusions, no isomorphism, just identity. If I have any gamma space, then it can be considered as gamma category. Wherefore, well, if I have gamma space A, generally, right? So then I can construct it tautologically a gamma category, but it's a category which is quite strange. The objects are also topological spaces. Actually, Sigal freely considers what we now call internal categories in topological spaces, not only enriched in topological spaces, not only when the homes are topological spaces, but for example, in other his papers, he freely uses what's called internal, so both morphisms, and it's not like DG categories where, say, objects are sets and homes are complexes, right? Here, both might be, yeah. Topologically, in that sense, we consider it as a gamma category. And why? We can do it just because only identity morphisms, and that's it. So then the objects are these topological spaces, and then the morphisms are identity. So clear, right? So, and then we can construct it in this way. So then I like to construct such a map of gamma categories. I would like to construct a map of gamma categories in this sense out of element A here. Yeah, so then for what is actually element here, yes, so this is from P of this row of K, this category should be mapped to finite sets, right? This is how, well, this how I define this gamma category. Here we have the joint unions, so inclusions, here it's another story, not like that. So then I now like to consider some interpretation of such map. So let me consider such map theta, and let us assume that from the entire set 1, 2, so on k, the image of this theta is n, some finite set with n elements, right? So this is a maximal set, so understand, right? So this is a maximal, which contains all k elements. It's like my A12, right? So this is like what's n plus m in that for n equal to. So this is actually n. So I mean, maybe you can see that it's n1 plus so on plus k, where theta of I is mi. So but doesn't matter. So then you consider that, and then all maps of in this category, all such maps can be interpreted as actually maps from this k to n in gamma. So these are objects. So the claim is that if you have such function in gamma where the element of k element subset is mapped to this n, is n actually, not mapped, but is this n element set, then actually I get the same information as for this functor theta. Then for any subset, as gamma gives me a morphism in gamma, defines me on any subset, so on. So then I can interpret this one as such a thing, right? So then it's actually where k, 1 to k is sent to n, entire n, and then some subsets are so on. Yeah, for example, I will be sent to ni in this notation. So I get exactly the same. And what now are the morphisms? Morphisms are isomorphisms in gamma. So the morphisms are such diagrams n, where here I have isomorphism. These are morphisms in these categories. So this is isomorphism, and this is some two morphisms in gamma, such that their image is image in that sense from k element set is entire n. So this is how I interpret these guys here, right? So then for each such map from k to n in gamma, for each such morphism, I have a map from a of n to a of k. This I have in general, but now let me consider this situation, particular situation where I have a0. Then this one is just equal to a1 in power n, and I may consider element with sequence of n elements among which each of which is a. So then to where it is mapped. Clearly in this notation where theta of I is ni, it's mapped to a n1, a n2, so on, a n k. Right? Because it's how we defined for this particular monoid gamma space, how we defined the action on gamma. So we take just the product of all elements of this subset. You remember, so the formula was that if I have, say, n1 to n to m.
This exercise that you gave.
Yes, okay. You remember?
Yeah.
Should I repeat? Should I repeat how it?
The product is universal. The product of ones is like n.
Yes. So then it follows like that, because I take, for example, if I have here the place I, some element i's position, then I take theta of I, which is subset of n, and then I should take the product of all elements which belong to that one. That was the formula. So now I have all elements A, so then I take products of A of these elements and get this formula. But what is amazing here is that actually this commutative diagram, which is a morphism, implies that I have A of n here, A of n, and they commute to the map to A of k. Just because this diagram is commutative, it remains commutative after I apply the functor A, gamma space. So that it means that any morphism is mapped to identity morphism here. So that I indeed get a map of gamma categories from this to this, where this I consider as gamma category tautologically with only identity morphisms. Clear, right? So because just this commutative diagram, it's somehow strange, but it happened that this diagram is commutative, and after this interpretation, I get actually this map on the level of gamma categories, for which here the gamma category structure has only identity morphisms. So now I pass to B, then it gives me B sigma k, B sigma to A, and I'm done, right, for this particular case.
Yes.
So then for any A from any A of A1, I take some. Yeah, in principle, you can say that I have to prove that for different representatives of this class, I have equal maps or homotopic. But let me do it later in general case. I have.
Could it be that in the category beautiful A?
Yes.
The collection of gamma spaces that are generated like in this slide by M commutative monoids are from a terminal.
That's a bit confused.
So could it
maybe after mapped out, please, yes, because I have to do that. Yes, so then the idea is now what I have to do. Yeah, so let me fix here, let me say here that here it's not done completely, because then I have to prove that if A and A prime are connected by a path in this topological space, I have to prove that these guys are homotopic, right? So, but now I consider general case, where A is any special gamma space. So then A special gamma space, and I have A which belongs to pi 0 of A1. So in principle I like to mimic the same speculation, but the matter is that why I cannot mimic it. Because taking A here I have only homotopy equivalence. So then I cannot lift it to AN, right? So then what Sigal does, actually he little bit modifies the construction B sigma in the following sense. He now maybe it will be a bit strange to say it in the very end, but anyway, this is the idea, I explained the idea, and now it's a claim how we can consider the general case out of this idea. So this is homotopy equivalence for general special gamma space. So I like to consider a homotopy fiber of that. So then let me Fa of n would be homotopy fiber of An to A1 in power n. Yeah, so I can recall that it's actually An direct product over A1 in power n with path of A1 in power n. So then I hope that this is known, right? That we can have this formula with path object exists. So well, then I claim actually that this gives me a functor from finite sets and inclusions opposite to top, such that the direct sum such that f, this is some functor f, such that f of s union with t is homotopic, the canonical map to f of s product with f of t is homotopy equivalent. So then it's some additional data. So somehow I like to work, I like to, well, lift this point to this an, but as I cannot lift it, I actually like to put here some homotopy fiber, and then I can lift it anyhow. I can take any point of the homotopy fiber. So then the construction actually, then I modify for each such f. I consider, well, this sigma f instead of this sigma, which actually of k, yeah, so it's also gamma category, where the objects and morphisms are topological spaces in Sigal style. And in this gamma category, we have the following, that similarly to here, a morphism is, an object is a map from k to n, such that 1, so on, k is mapped to n, right? And also a pair, and then x, which belongs to f of n. So the element here. So well, the simplest example of such functor is f of n is x in power n, where x is any topological space, not necessarily based. Then if I have n0 included to n, then of course I can project on some coordinates and get a functor from xn to map from xn to xn0, just projection. And then this map would be isomorphism, not homotopy equivalence, but just because I have here xs plus t, and here I have xs, now xt in this case. But in general, I require it to be homotopy equivalence. Yeah, and then I consider the following category. So the object of this category is so the objects are these maps k to n, such that the image of 1 to k is n, and some x in f of n, some element. So then somehow I can also, so the claim is that it's a gamma category, is a gamma category because when I have some subset, say some I1, so I L in K, then I can actually, well, on this guys, I have the structure of gamma category as before, but also I can restrict Fn to the corresponding, so then I have Fn to the corresponding F of n I1 or I1 plus n I L. So then I can restrict this F, and this, I mean the this gamma category structure is defined in this strange single sense. So then it is applied to the homotopy fiber. One has to show that homotopy fiber gives me a functor from finite sets inclusions to topological space with this property. So it could be easily explained, but let me skip this. It's really easy, so just exercise, you can ask me if you are interested. So, but it's just to save the time, because I'm running out of time. So then the idea is that if I have, so then I like, in general case, I like to construct, so then let A be indeed pi 0 of A1, then out of that I am going to construct a similar thing, but where here I have sigma F. Sigma F, I constructed to a map of gamma categories, similarly as I did here for without F. So this is gamma category, which for without F is just sigma, right? So which we construct. Now I introduce here F in this way, where F will be the homotopy fiber of a fixed point A. Because I have no canonical way of lifting this point to here, I consider the entire homotopy fiber. So then I claim that any A gives me in the similar way to there a functor of gamma categories. So then here it's only identity morphism. So this is gamma space, which I tautologically make gamma category. And actually the idea is very similar to what I have here, because yeah, it can be said something like that we have Fa of n, as it is homotopical fiber, it is mapped to A of n. Yeah, if I have this map from, well, n, the same diagram as before, K, n, K isomorphism, n again. Now I decorate it as follows, so it's mapped to A of K. Yes, and then I have here, if I have any morphism, which is isomorphism, then I get such diagram like that. Here n, here A of n, then this, and this is commutative. So this is commutative because this is commutative, and this is commutative because f is a functor. Yeah, so then I have something like that I still can, from this commutativity, I can just take any point in this homotopy fiber, so then it gives me a point in this category decorated with f, yes, with this homotopy fiber, and then actually I can literally repeat the same construction, really. Well, unfortunately, I'm running out of time, so then after that, actually, this is done for some particular choice of the representative, and only what remains to do is to prove that if I have A and A prime connected by a path alpha, then I can really construct something which you did not like. What here is A, here B sigma F A prime, so here I have, yeah, so this is important that these are actually Hurevich vibrations with fibers weak equivalence, because I assume that A is special, and then these homotopy fibers are all contractible. So in my case, all these F are contractible topological spaces. So here I have B sigma, so I just replace it by a head, right? And this is mapped to A. So then I have constructed such two loops for particular choices A and A prime. Elements A and A, this is not that, A and A prime are elements in A1, which represent the same element in pi 0. And now I actually connect them with a path alpha and put here something like B sigma, well, tilde with some diagram, which actually is also commutative, which like that, which is commutative. And for this, well, the sigma, I put another F prime, which is actually the fiber point of this, so then I have something like, just a second, I have something like, for this B sigma, I consider the same stuff of category B sigma F prime, where now F prime is somehow the homotopical pullback of this F prime of n is homotopical pullback of this diagram of here it's n, here it's alpha n, alpha dispersed in power n to a1 in power n, and here it's a of n. So then before I consider the point here and got a homotopy fiber, I have two different points and I have a homotopy fiber, then I connect them by pass and consider more general homotopy pullback. And then I can put such guy here and prove that I get such a diagram, and then actually this is why I told you last time these technical things, because actually it's not commutative, but commutative only up to homotopy, in fact, if you work out details, and then this commutativity up to homotopy and the fact that we can define the homotopy category of gamma spaces in this way, it's actually it's a manifestation of general phenomenon, what is called the category of fibrant objects, which I probably very unsuccessfully tried to tell you yesterday. It was about that. So because actually we want to deduce everything to like in derived category. So the morphisms in some category we work with are such maps like that, such roofs where two different roofs are W prime, F prime equivalent if we have such maps where these are also weak equivalences, right? And then some not weak equivalence, some F prime, and then actually this particular story looks like this diagram for which you prove that two morphisms in derived category are equivalent. So the message is that the same way how Verdier defined the localization by quasi-isomorphism, so definition of derived category. Firstly, he did a homotopy category of complexes, and in this homotopy category of complexes, the quasi-isomorphism satisfy the right fractions, and we can do it with all this Roof's calculus, right? That this phenomenon is very general, and Sigal implicitly uses this fact, which appeared more or less in the same time, and in fact, it's called in any model category in which each object is fibrant, and more generally in any what is called category of fibrant objects. So this is a particular case of this general thing, and this is why we can actually firstly consider homotopous classes of maps of gamma spaces in a very literal way. Yes, and then in that case we can consider these left parts of the roof either as weak equivalent, either as homotopy equivalents or as Gurevich vibrations with actually trivial vibrations somehow, which in our case is Gurevich vibrations with trivial fibers. So this example with Fi gives me exactly Gurevich vibration with trivial fiber, and this is how it works. So then sorry that I said a bit later.
Let's maybe questions.
I have a question.
Yes.
But you showed us this adjunction between B and R, and B looks something like a tensor product, and R looks like something like a form. So to me,
so you mean probably this, right? That's step of B.
Yes, exactly.
Of some A or say B sigma, I said, right? But doesn't matter. And then here X is in A. This from B sigma to Rx, right? So
yeah,
we're talking about that, right?
Is there anything special about? Basically, to me, it seems like it's tensor Hom adjunction in the category of
topological space,
sector valued with sheets on gamma. Is there anything special about gamma here?
Absolutely nothing. Absolutely nothing. The only special is that. Look. As I actually I think the lecture previous to the second lecture, I think I explained it in detail. So then basically basically, so how we establish this junction actually? So first of all, we do it on the nose, and then I will not focus on how we descended to homotopy level. So on the nose, right, we firstly prove that B of any gamma space, which is a spectrum of say A of 1, right, B. A of 1 somehow and so on, is can be alternatively, so B2, well, A1, Bn1, however, so it can be alternatively defined as, so the BK, the case, this classifying space of A is SK, what I call SK dot, which I call product over gamma with this A. So this is coherent, and this is canonical gamma space, which I associate with any topological space, or in particular any spectrum, any topological space with base point, or any spectra with base point, and so on. Probably you remember, so this is gamma space. So it's not gamma space, sorry, it's a functor for any topological space. This one with base point, this is a functor from gamma to topological spaces where P of n is this P just in Cartesian power n. So what I proved by Anderson argument, that actually if I apply this construction, a general construction, then it's coherent, right? This is functor from gamma up to top, this is functor from gamma to top, and I can consider coherent like in definition of realization. So we proved that, well, in the end of second lecture, I guess, that in this way we get exactly that. And that's only what we needed. So after that, we can take here any space P, for example, and then, well, here we only, it's also important that the spheres form a spectrum, right? This is also important. And then actually this is quite formal, because look, then what we have in Rx, this is a spectrum, right, whose nth component is, no, sorry, it's gamma space, I'm sorry, whose nth component is home from the sphere spectrum in power n, Cartesian power n, to x. This takes values in top. So this I more or less explained what it is. And somehow you incorporate the internal home in topological space and take that part which is compatible with the structure maps of spectra. So basically this is by definition the internal home of two spectra, x, y.
I think you're reproving why this works for gamma and not answering the question.
No, I just said, you asked me why this junction holds. I said,
no, this is not
I'm
the
sorry.
question.
Yeah.
I asked whether there is anything special about gamma.
Special about gamma is that I can't rewrite this one, this sequence of classified space or this spectrum. Yeah, exactly, I answer in your question. So I understood it correctly. So what is special for gamma? That I can rewrite it in such a way. But as soon as I have any other spectrum instead of Z written in such a way out from some any spectrum Y, so then instead of these spheres I can replace that sphere spectrum with any spectrum Y. Then I can define B tilde, I would say K of A, as this Y, say dot whatsoever A, so on. And here instead of sphere spectrum I can take this spectrum Y in power n, and this would work. So only special about this I can do for any Y instead of sphere spectrum, but what I use, especially in this construction, is that this one has very gamma categorical meaning, gamma spacing meaning, namely this is this sequence of realizations, right, as I explained. And then in this particular case for gamma, we can rewrite it as in this way. But as soon as we can rewrite it in this way for some spectrum instead of the sphere spectrum, then it's absolutely general phenomenon which comes literally from the junction in this topological. I even actually, I think I tried to maybe I said it a bit chaotically, but I actually even prepared to write it down somehow that you can say.
I don't think you should do it now.
Yeah, okay, then spectra from maybe this you can say A times any y, then to x is the same that gamma spaces from A to this, well, home of y to x. So this is actually a general adjunction which holds for any spectrum alpha. And what is specific for our situation, then this for y equal to sphere spectrum is coincide with this spectrum of geometrical realizations. That's it. So after you have that, it's absolutely general phenomenon, right? But this we proved it actually, I think, in a nice way during this Anderson argument, which is quite different from Sigala argument.
Okay.
Yeah.
Sorry for taking long. Maybe other questions
Oh.
after lectures.
Or maybe
Ah,
we'll discuss
ah.
it.
Yes.
Yep.
Said